Thank you, Jonathan. I'm Minnie. I work with an organization, Celestica, as a security architect into product development, engineering, R&D, more focused on embedded system security, hardware supported security. And that is the current role. And over the period of time in the industry, I have worked in various domains. A whole lot of it in the embedded system product development, hardware supported security, supply chain security, and those kind of topics. I've been quite active into the security world, both in these kind of events or even publishing or filing patents, all those kind of activities I keep doing. And education wise, I am also doing my PhD currently. So let us start. I hope the screen is visible. So what we will be covering today is Internet of Things, very specifically the industrial Internet of Things. In the supply chain of hardware physical components, how do we secure the hardware components in the supply chain? That is from a manufacturer till your deployment and in your running system as an owner operator, and also when you discard the device, what do you do? So across this entire life cycle, how do we take care of the security from physical devices? That is what we are going to cover today. So Internet of Things, when you see here, I have put some kind of representative Internet of Things. They are quite heterogeneous entities, the things which we call in an industrial world, OT world, we may be talking of your IEDs, RTUs, PLCs, or even your sensors, all those kind of physical devices. Or in the smart cities, it can also be your sensors, controllers, all those can be the item. And typically what happens is when you connect this Internet of Things, they don't do a standalone. They will be communicating to some kind of a software entity or a cloud hosted entity on which you will be running your application. See, I've put a representation that locally there would be usually a local network that you will use. It can be some kind of Ethernet, Bluetooth, Wi-Fi, some kind of local network on which they all communicate. And the local network and the internet boundary, typically there would be some kind of a hardened point which will be taking care of this communication, which is an edge gateway. And then from the edge, it goes to the cloud, and you may be running applications on the cloud to understand. There could be various operators who are working on this. It can be human operators, it can be software applications who are interacting with all this. So we are talking about the things on the left side. And in this kind of a network environment, how can we make sure that the security of all these components are taken care across the life cycle of the device? That's what we are trying to talk in this session. Okay, so let us look at a typical device life cycle. See, first it will get manufactured. Till manufacturing, there are so many other components that will come in. There can be ICs, there can be TPM, there can be other subcomponents, all that will come in. That's not what I'm talking. We're talking about from the point of physical manufacture. So again, we have to take care of the IC supply chain compromise, the semiconductor supply chain compromise. That's not the portion which I'm covering here, considering an OT security context. And further, it gets into the supply chain. Supply chain, it can be your multiple actors in between. It can be your system integrators. They will take various components from various manufacturers, various vendors, and then put them together a system. That can be one. But then provision is something which will be happening in the ultimate system on which it will be actually doing its primary functionality. In the owner operators domain is where the provision is securely. How do you provision this? So for example, when you get a say a sensor or a PLC, and then you are putting into a system, how do you know that, okay, this is indeed that, it's not a counterfeit component, it's really what we want? How do we know about all that? That is what we are trying to ensure in this process. Okay. And during provision, we have to verify that, okay, this is the device which I want, and at the same time, is this the device which is supposed to join this network, and then only join. And all these cannot happen. There are quite a lot of cryptographic activities that happen here, exchanges, verification, and all this cannot happen with the human beings verifying, because the reason is we are talking of cryptographic verification during the provisioning process. Because human verification means you need that kind of a talent, and even with the talent, we are talking of key material, and those kind of verification has to happen via automatic mechanisms. So automatically provisioning these kind of physical devices into a network, and then you are doing your operation. During the operation, you will have various other management activities that happen on this device. Say, for example, there could be a firmware update that comes, there may be patches that will come, or there may be configuration update that can happen. There can be parts replacement that can happen. So how do you replace the parts, securely replace the part? It's not that a malicious component is coming as a part and then we are replacing it. That should not happen. And finally, decommission, how do you do the sanitization? How will clear up the data, sensitive data inside? If there is any key material that the owner operator has provided into it, how do we clean up that? All those kind of sanitization of your memory and all other area. That's what configuration, key material, customer information, sensitive information, everything. That's what we are talking in the decommissioning. So this is all the entire cycle that we are talking in a device life cycle. And today our focus, I would try to focus on the provisioning step and how all other steps can go along with the provisioning steps. Provisioning, onboarding, all those are terms that are used in a very interchangeable manner in this context which I'm talking about. Okay. And the thing life cycle, which we talked, a different view of the same thing life cycle. So what can happen is initially it is manufactured, they go through various states. So it is manufactured, then it is installed, commissioned, then there are applications running on it. And then it can happen that software updates can happen. The initial bootstrapping, that's the initial phase. Then there is operational phase where the intended functionality is working. Intended functionality means if it is a temperature sensor, actually measuring the temperature. And then the application may get reconfigured. And again, the application may be running further in an operational mode. This maintenance and bootstrapping can happen in between. Decommission can be there. Then you can also be that you remove them entirely or you may replace them. And there is also a case of re-ownership or recommissioning. That means you can take a used physical device and then you are taking it and putting it into another environment. You can resell it again, refurbish and resell it again. So that's also one scenario. In all these conditions, no sensitive information should go further from your hand. At the same time, you have to be able to make sure that this is not a counterfeit, this is genuine component across the supply chain, no tampering has happened. All that is what we have to do, both in the operational time. Say operational time, you get a software for update, a firmware update. That firmware is good. We have to verify that it is a genuine firmware that we are updating. All that has to happen. That's what we are trying to talk here. And in this process, how can all this happen with the support from the hardware? Because when we tell these kind of security requirement, it's not possible to achieve all these only via software means. Software firmware means it's not possible. We need underlying hardware support also. Say, for example, a secure boot, or if there is a sensitive information such as a private keys, how do you store them securely? It's not enough to put it into any memory area. We need a secure element underlying, something very similar to TPM, trusted platform module, that can generate keys and store them and only do operations on that without ever anyone be able to get the private key out of that chip and in hand. So we need kind of secure elements to store them and root of trust to take care of the boot sequence. All that is required. Okay. Now to go to this concept a little further, we will look at some of the security threats. These are only examples. I am not talking in exhaustive manner. There are various security threats can happen. A vulnerable software. Vulnerable software, typically in the software, there would be some CVEs which may be there, known to the public, but then the next version would have already patched and updated. Patches may be available, but it can be a vulnerable software. You should not go and update with a vulnerable software. And there can be privacy threat. Say someone can be tracking the location, traffic interception, all that can happen. Key material can be collected. All that should not happen. Cloning is something which is the solutions which I'm going to talk about will very well take care of the cloning. It may have a look and feel of the original device, but they are not coming from the original device vendor. They may be cloned, and the cloned devices may have the same look and feel, but it may have a degraded functionality. It may be coming from untrusted factories. It may be having backdoors inside, though it may look the same. And it can be counterfeit. That's what we are talking. It should not be counterfeit. If you say that a genuine vendor is giving, you should know that, okay, it is coming from a genuine vendor. So how to do these kind of verifications? And some of the threats which I'm talking is replacing a genuine component with a low quality one. It can, from a very minimum, it can also be a damage to the reputation of the original device vendor. It can also be malicious, as I was telling, and eavesdropping should not happen. There can be a person in the middle kind of an attack, which can happen at any time during the commissioning, during operation, all that it can happen. And firmware attack. Firmware attack can be a maliciously replace a firmware other than the original firmware which is delivered by the original device vendor, the genuine device vendor. It may be some other malicious firmware that you are allowing an update into it, and no extraction. Uh, these devices may be often physically unprotected. See, if you are talking of an industrial automation or an operation OT technologies, they are not always kept in any kind of a lock and key. They can also be deployed in the public places. So they are not physically protected. So our goal is that even if someone gets physical access, it should not be possible to launch any of this kind of attack even after getting a physical access to the device. And denial of service, which I believe many of you will be already familiar. Elevation of privilege routing. These are all the kind of some of the attacks which I'm telling. I hope you get an idea of what is that we are talking about now. So this is the top security vulnerabilities that you are talking. Say these are typical errors which people keep. Lack of device management. You don't keep it up to date. The transfer and storage may not be right. The default settings are not right. These are all kind of issues which all these should be taken care in the supply chain of the physical hardware. Like whether it is by the integrators, device manufacturers, is the secure by default handled or is it not done? All that is the cases. So now with these kind of security threats, how can we take care? See, I believe you must be already knowing with the stories of, see, we keep telling these to small children. One such a story is a fairy tale story of the Little Red Riding Hood. They'll tell, okay, the wolf will come and then tell the Little Red Riding Hood that, okay, you see how pretty these flowers are. Why not you have a look around? And then she goes to fetch the flowers, but ultimately what happens is the wolf will go and then the wolf will put the grandma's clothes blankets over the wolf and then will be lying there. So the Little Red Riding Hood think that, okay, that is the grandma, and then she gets swallowed by the wolf. That's how the story goes. But if you recollect these stories, originally when this Riding Hood's mother sends her, she gives an instruction, don't talk to strangers. That was an instruction given. But then it was never told to her. How do you recognize that, okay, is this a stranger or not? See, she did not know how to make out who is a stranger. So it can so happen that even after an instruction is there, you do not know how to do it. So this is what we are going to address here. How do you know that it is a strange device? How do you know that it is coming from genuine? How do you know whether it is full for grandma? How do you know whether it is malicious or otherwise? So we will start off with one fundamental assumption that we have to achieve if you have to do these kind of secure physical devices. We need to have something called a root of trust. A root of trust means when you boot the firmware, when you boot the device, the firmware get uploaded. One by one, it gets loaded and it goes. And in this process, how do you know that there is something which is a root of trust as an anchor so that every other firmware running on it is good? So typically what happens is this is a hardware supported way of achieving security of the physical device. So this root of trust will make sure that you are not allowed to run any firmware component, whether it is operating system, mutable code, application, anything, your UEFI secure boot and those kind of topics is what I'm coming to. It's not possible to load any firmware, any mutable firmware, unless you are able to verify that it is genuine. That is what we will achieve by this root of trust. So typically what happens in a boot process is you do power on, and then you will have an immutable code, which is a ROM code that will take and verify the first mutable code that it is fine, it is good. So to do that, there would be hardware supported OTPs or eFuses, which is the hash of the public key used for signing the first mutable code into the hardware itself. And once it is burned into the hardware, you can never change. So we depend on those immutable parts which are implicitly trusted, the immutable boot ROM and the immutable eFuses. They are implicitly trusted, and then you go further. So the first mutable code is verified with those OTP signature to know that, okay, this has a signature, and then you load the mutable firmware code. And then the mutable firmware code, first mutable code, can also contain some additional public keys that you can use for verifying operating system. And then your UEFI can take charge, and then you can go further and then do your application. So once you are able to make sure that the first mutable code is verified by the hardware and then loaded, you know that, okay, I have the capability to verify all the other code further and then do it. That is what we call as a root of trust. So based on this root of trust, everything will happen. If a physical device does not have a root of trust, it's a possibility that you can intercept the supply chain and then intercept the boot process, and then you can load any other malicious firmware. So if you don't have a root of trust, no, we were not able to achieve that. So this one require a hardware support. Similarly, let us come to device identities. So I was always telling, how do you make sure that, okay, it is coming from the genuine manufacturer? So typically these are achieved with the hardware supported device identities. So device identities are, you will have a public private key pair and an associated certificate signed by the manufacturer. So whoever is a manufacturer, they will put an identity key pair and an associated certificate into the device, and the key is protected by a secure element within the device. So there is a private key, public key pair within every instance of the device. This is the instance specific identification, which is also traceable to the manufacturer because they are signed using the manufacturer certificate. And there is a certificate chain which is rooted on the manufacturer CA. And when you are manufacturing, you install an IDA. This is called an IDA. Some people call it a birth certificate, an initial device identifier, a fingerprint certificate, such kind of terms. I think DigiCert was calling it an evergreen certificate at some time. All that is put in, then you ship it. So at the time of shipping, and then once you receive it, you install, you receive it, once you provision it, when you provision, whatever you got from the manufacturer domain, they are not valid in your current operating domain. So you need to have identities in the operational domain if you have to communicate with the device, because manufacturer domain, you cannot use for communication because they are not trusted here. Because say, for example, if you have a local network, they should be able to talk to each other, but not from the manufacturer. So you use this manufacturer installed identity to give it a new ID, which is called an LDAV ID, or a locally significant identifier. And that's what the process which we call as a provisioning. In this provisioning process, the device is verified that it is indeed genuine and it comes from genuine manufacturer. Also, the device can verify, am I joining to this network which I'm supposed to join? In the sense that if your device is not sold to that specific customer network, it can refuse to join to that network, and it can say that, okay, no, I'm not going to work in, this is not the home where I'm supposed to be joining. That's also a possibility in the provisioning process. So ultimately, you will get an LDAV ID, which is another public private key pair, which will be with an associated certificate. That certificate will be signed by the operational domain CA. And then let us talk about some protocols for provisioning. In fact, this was the intent of the talk which we are coming to. When we provision protocols, there are standard reference protocols available. I will explain to you one or two protocols here, which are commonly used in this domain. It's not that they are also heavily widely deployed. They are upcoming. They are deployed in many contexts. They are deployed. Many are still trying to do that. Some are trying to get the setup ready, because it is not just about a software. You need to have factory ready for providing the IDA ID, and you need to have other infrastructure elements like your servers to set up all this so that you can do this provisioning, onboarding, automatic. We are not talking about human intervention, automatic provision. So what happens is, you take a physical device, you take it, you plug it onto a network, it gets an IP address and it gets an identity, and then it joins the network. It is trusted by other network. All that happens seamlessly without human intervention. And especially in the OT network, you don't have talents who can do, say, you tell that we call it as the wrench and screwdriver engineers. If they are able to physically connect a device, it should work securely. So that's what we are trying to achieve by doing all that. It's not that all will be experts in the digital certificate or cryptography are not the ones who are really working in the field. So field engineers should be able to work, but at the same time, it should be secure. That's what we are trying to do. And then these onboarding protocols, what typically happens is, from the manufacturer domain, you have an IDA ID, and the onboarding protocol will work such that you will get an operational domain LDAV ID. And when you do this, there would be infrastructure required in the operational domain. There would also be infrastructure required in the manufacturer domain. And they are linked together by something which we call as vouchers. There are various provisioning protocol. Typically, we call it as a voucher. IATF has given the name voucher for that. OPCUA gave a different name. They are called tickets, vouchers. All those are similar data. That is a data, a file artifact, which will contain identity of the device and the identity of the domain in which the device is going to join. And they are signed, the voucher itself is signed by the manufacturer. Like as part of an order handling process or an order fulfillment, you can sign the voucher and give it. So once you have received these two, from the voucher, you know this is the device which is supposed to join this network. And the device can understand that, okay, I'm supposed to join this network only. All those kind of information you can make out. So what happens in the process is, you will have a device authentication and device authorization. You have a secure credentialing. That is where you get an LDAV ID. And then there is a network authentication and network authorization that happen from the device side. After all this is done, you will get identities in the local domain. Typically, the device generates a certificate signing request CSR, and then it gives to the CA, local CA. CA will sign it, return it. You got a local certificate. So there are multiple provisioning protocols. Two popular ones I will explain here. FIDO device onboarding, FDO. This is quite popular one in the IoT world, which some people are also trying to do in the industrial automation world. But this is the one reference protocol which we can use for FIDO device onboarding. So here what happens is that there is a device initialize protocol that is a credentialing in the initial time. So that means when the manufacturer creates a device using the device initialize protocol, it will provide its birth certificate. So that gets its birth certificate and then it gets transferred to the owner. The owner is the one who is owning the operational network. And there is an ownership voucher also that is part of transferred as part of a supply chain. It's a file artifact, not a physical device, and that also goes to the owner. So the owner, on receiving it, will receive both the physical device as well as a voucher. Both together will come. And then you are trying to onboard the device. In that, there are three protocols that are run. We call it a transfer ownership protocol 012. And the transfer ownership protocol, we have a rendezvous server, which is a kind of an infrastructure server maintained by it may be maintained by various models, but it can be by the owner, can be, or it can also be some of these the device manufacturers can also be maintaining a rendezvous server meant for everyone. All that is possible choices, but there is a server to which both the owner network and the device will go. The owner network will run transfer ownership protocol 0, and that means the owner network is known to the rendezvous server from now on. And similarly, you run a TO1 protocol from the device. So all these kind of devices which are ready for FDO onboarding, they should be ready to run this TO1 protocol. They should be implemented inside, apart from the identities. So you run this TO1 and you register yourself and make yourself known to the rendezvous server. So once this is done, they will exchange certain information, and after that, both the device and the onboarding network, they can talk to each other. That is your TO2, that is a transfer ownership 2. So once all these protocols are run, this component, physical component, and the management agent and a service, one then the receiving network and the physical device, they can talk to each other in a trusted manner. Means you can run your TLS kind of protocols further. So this is the concept of a FIDO device onboarding. I would really recommend that you have a look at detailed about the FIDO device onboard specification. They are publicly available. So this is one protocol for device onboarding, which is quite highly used in the IoT world. And we will also look at one more protocol here. That is the OPC UA device onboarding. If you are looking at this, came out in the recent few years. It was not there from the original one. The thing is, this one takes care of the device life cycle, what typically happens in an industrial world, in an OT world. If you OPC UA part 21 device onboarding, that's the exact name of the specification. So you get a manufacturer, there can also be a composite builder. Say, for example, if you are machine builders, you may be taking components from various people and then assembling them together, and then you may be doing a machine building. And then you have an identity, which I talked about. For an individual component, there can be an identity, and for the composite also, there can be identity. So composite identities are possible. Then you come with a distribution, that is your distribution network, and then you come into the integrator. The integrator can do your onboarding application setup. Application setup means your PLC kind of programs and all possible, and then running your configuration, operation, and then decommissioning. This is completely covered in this OPC UA device onboarding protocol. And there they are also identifying that FDO can be an alternate authentication model in the OPC UA. And they call these the document artifact which I was talking about. That is they are called tickets. Tickets they usually bind to the receiving network and the individual physical component. This is what happens. I think for a summary, this is a summary that I'm talking. So we talked about how can manufacturer provide identities, what you should do there to ensure supply chain security, and what can happen in the supply chain during provisioning or during onboarding, what do you do? And on the operational side and management side, when you do firmware update, what has to happen? Decommission. This is what we covered here now. I think if there are any questions, we could attend to that.
Wow. Perfect timing. Thank you very much. Amazing amount of information in a short period of time. There is a question here, if that's all right. We should just have time for a minute or two response. So, hi, Minnie, can you please tell me how patch management will work if patches are available? Is it possible to do an online or offline?
Okay, this one, it's a bit sensitive question. To say that we are talking of critical infrastructure here, if we are talking of typical Windows IT network, you may be going and updating patches, but that the good practice of a patch management is we should qualify the patches first. So if you update the patch, will it spoil your system? Will it bring down your system? Or is it able to accept it and then be still running smoothly all the verified functionality before will it be working well or not? So typically what happens is you take the patches, then you see that okay, all you qualify the patches by doing local testing, and then you host all those patches on a system, on a network system like WSUS or those kind of servers, and from there individual devices can go and take the patches and update. That is a good practice. But even then you have to look for the downtime, because patch management always is not a background activity. Sometimes it may ask for a reboot and all that, so we have to consider the downtime. So online direct update for a critical infrastructure, that's not the recommended way, because it's not safe to do, because all these systems which we are talking, they are also safety critical system. It's not that once it goes down, it's not just a reduced functionality there, it can also be affecting the safety of your network. They are critical, that's what we are talking. So online update directly, online, you can still call it online, but it may be a locally hosted verified and qualified patches.
Right, and it's assuming you get the patch from the actual vendor as opposed to from the
Yeah.
operating system. Fantastic. Well, thank you so much. That was a very informative discussion. Really appreciate your time, Mine,
Thank
and
you.
the audience.